So, again, I apologize for being gone Friday. I had to go to the National ACS meeting. I serve on a national committee there. It's required that I go twice a year. But you had a substitute. I hope everything went well. It kind of put us a little bit behind in the sense that today was supposed to be an inverted lecture. We're going to move that material to Wednesday. I'd kind of anticipated it, that this would probably happen, and that's why I put in there the problem-solving session on Wednesday. So we'll take care of all that stuff on Wednesday. So today we're going to just do kind of a normal lecture. Feel free to discuss as we get to various points. I want this to be an active learning environment, not a me talk, you listen kind of situation. Okay, so feel free to stop me at any point. So today we've got several learning goals. Today we're going to learn about resonance structures. How many of you remember what resonance structures were from general chemistry? Okay, so why do we need resonance structures? Let me ask that real quick. That's right. Lewis structures have inherently a defect. What is that? Electron positions are fixed. We assign electrons to atoms, and we know that not all electrons, right, belong to single atoms. Now, if you have a single bond, for example, those electrons are between those two atoms. But lone pairs, for example, if you have the right kind of motif, like a double bond and then an atom with a pair of electrons, we can move those electrons around and create different resonance structures or different hybrids. So we're going to talk a little bit about why we need resonance structures and what are some of the basic rules of resonance structures. We are not going to give you every rule you possibly need today. We will get that as we get more and more experience in drawing Lewis structures and drawing resonance structures. Resonance structures, the ability to draw structures, those types of things are very, very key to this course. You have to not only be able to draw a proper Lewis structure, you have to be able to draw it with the electrons where they need to be, and you need to be able to draw that Lewis structure in 3 dimensions. So we're going to add a little bit of an extra layer to Lewis structures that you probably didn't go into much depth in general chemistry. You did some things in 3 dimensions, but it was kind of just a piece of what you were doing. Everything in organic chemistry is 3-dimensional. Okay? It's extremely important that you understand structure of these molecules. We're going to then talk a little bit about orbital hybridization. How many of you liked orbitals in general chemistry? Nobody raises their hand. The reason is you all dealt with the vast majority of the periodic table. You were dealing with d orbitals, f orbitals, s, p's, right? In organic chemistry, we're largely only dealing with s orbitals and p orbitals, and that's because we're largely only dealing with carbon, right? So the orbital diagrams that we deal with are relatively simple, but they're very, very powerful. And knowing things about orbital hybridization allows us to understand the shapes of molecules, allows us to understand how they're going to react, allows us to be able to identify functional groups. And functional groups is what we're going to get into next chapter, right? And you're going to have to memorize a bunch of functional groups, but functional groups have their function because of their shape and their structure. Okay, so again, very, very important. And then we're going to talk about some structural formulas today. Condensed structures, skeletal structures, rules. There are certain things that organic chemists assume, and you need to know what those assumptions are. Okay? Organic chemists use shorthand when we are writing. We don't draw every atom out, nor do we draw every electron out. And you have to be able to know what our assumptions are in the language that we're using. So I just want to mention real quick here, this was my first graduate student, Del Rosato, when he went to Philadelphia for an ACS meeting many, many years ago. And you probably don't know who this gentleman is. That is John Fenn, who was a Nobel Prize winner back in the early 2000s, I think 2001, 2002. And my graduate student got to meet with him. And I like showing this because DJ, as we called my graduate student, he said, our rock stars aren't like your rock stars. And actually, Dr. Fenn was one of his rock stars because DJ was working an awful lot on mass spectrometry at the time, which is something we'll learn about in chapter 9 in this course. And what you see behind you is like the first mass spectrometer similar to the type that DJ used. And so it was kind of cool being able to go to the museum and see that and actually meet the guy who won the Nobel Prize. So in chemistry, a lot of students get to do a lot of traveling and see a lot of interesting things. And so think about that as you think about where you might want to do research. You might end up at a meeting and meet somebody really famous. Okay. So again, we had somebody say earlier that some molecules cannot be adequately represented by a single Lewis structure. If we look at the Lewis structure on the left and we look at the Lewis structure on the right, what are the differences? What distinguishes the left from the right here? Pardon? Okay, yeah. So we have a charge, a formal negative charge on the nitrogen in this particular Lewis structure. And over here we have it on the oxygen, even though it's kind of cut off there, right? We have it on the oxygen atom. So if we think about this, which one of those resonance structures would you suspect would be the major contributor to the overall resonance hybrid? The one on the left or the one on the right? The one on the right. Why? Not less negative, it's more electronegative, right? And so we know that electrons like to be on atoms that are more electronegative, right? That means that that atom has kind of an affinity for electrons, if you will. Now I'm using that term loosely because electron affinity to my physical chemistry friends has a very different meaning than how I'm using it here, okay? But it likes the electrons, it pulls them close to the nucleus, right? And so if you're an electron, are you going to want to be far away from the nucleus or close to the nucleus? Think about your basic physics. You're going to want to be close to the nucleus, and why is that? Yeah, opposite charges attract, right? So if I can take an electron and get it closer to the nucleus, it's closer to positive charge, that should be more stable, and in fact that's the case. And again, my physics friends will flip over that explanation, but that is really it in a nutshell, okay? If you think about just the basic opposites attract that you learned about in high school, okay? I want to point out that these electrons on the left, they are assigned to specific atoms, and so the charges are assigned to specific atoms. The electrons here are assigned to specific atoms, and the charges are assigned to specific atoms. But if I gave you a magic microscope where you could actually look at this structure, what would it look like? Would it look like the one on the left or the one on the right or somewhere in between? Somewhere in between. But it would look more like which one, the one on the left or the one on the right? Look like more like on the one on the right. And so we would call that the major resonance contributor. We would notice it through our magic microscope that the carbon-nitrogen bond is actually a little shorter than a typical carbon-nitrogen single bond, right? But not quite as short as a carbon-nitrogen double bond. And we would notice that the oxygen has a significant amount of negative charge, and the nitrogen has some negative charge associated with it. That's what we would be able to see, okay? And so these are called resonance structures. And notice we are using a double-headed arrow, and I want everybody to understand this, and I have to repeat this many times throughout this course. That double-headed arrow is not an equilibrium. These resonance structures are not bouncing back and forth between one another. These are defects in Lewis structures. But that's not what, the molecule doesn't look like this, nor does it look like that. It looks like something in between, and it's just hard to draw using proper Lewis structures. So we have to draw resonance structures, okay? So in drawing resonance structures, what can I move and what can't I move? I can move electrons, but I can't move atoms. I can move electrons, I can move charges, but I cannot move atoms. Once I have moved an atom, I'm doing chemistry, okay? So that's no longer a resonance structure, okay? We're only dealing with resonance structure, okay? And so again, here we have the two resonance structures. What really exists is what's called the resonance hybrid. And the hybrids will show characteristics of both structures. The hybrid quite frequently is not easy to draw, and so that's why we're stuck with this Lewis structure formalization, okay? We say that a pair of electrons over these two structures is delocalized, right? The electrons here can be delocalized to the oxygen, and the electrons on the oxygen can be delocalized back to the nitrogen, right? Those electrons, those two electrons, or that electron pair, right, doesn't really belong to either of those atoms. It is delocalized over that system, okay? One of the things that you need to remember from general chemistry is anytime you can draw resonance structures and delocalize electrons, that stabilizes the system. By definition, the more resonance structures you can draw, the more stable the system, okay? And that's going to become very, very important as we move on and start talking about chemistry, okay? I mean, the actual chemistry of organic molecules, okay? Reactions is going to be very important. And so you'll hear me say things like resonance stabilization or resonance stabilized, those types of things, okay? So let's take an inorganic molecule that you probably should remember from general chemistry, carbonate. The carbonate anion, CO3 2 minus, right? And if I was to tell you to draw the resonance structure for this, how would you begin? Carbon is the central atom. And why is carbon the central atom? Pardon? It can form a lot of bonds. That's true. That's part of it. What else? When you did your when you did your laboratory on resonance structures, what did Ms. Masterson always tell you? Which atom becomes the central atom most of the time? Well, in general, the most electronegative or the least electronegative? The least electronegative atom typically is the central atom in a Lewis structure, right? Carbon is less electronegative than oxygen, right? We remember that rule, right? We can add up all the valence electrons. Remember, we're only interested in the valence electrons. Why are chemists only interested in the valence electrons? Those are the ones that do the chemistry. That's exactly right. All the other electrons, and again, my physical chemistry friends will shun me for this, but all the other electrons are just placeholders for the valence. As far as I'm concerned as an organic chemist, the valence electrons are all important. Okay, the internal electrons are just there taking up space, okay, and allowing those valence electrons to be where they're at. So there are 24 valence electrons. We know that we are going to have a central carbon atom. We're going to have 3 oxygens, right? What's the shape of this going to be? Trigonal planar, right? And we know that there's going to be a carbon-oxygen double bond, 2 carbon-oxygen single bonds. And so if we were looking through our magic microscope at this, what would we see? If we had just this one resonance structure, we would see 2 carbon-oxygen bonds of equal length that are longer than the carbon-oxygen double bond. And we would see that those 2 oxygens down here on the bottom are negatively charged. However, if I could really give you that magic microscope, and by the way, that magic microscope is called X-ray crystallography, and we can do this, what you would find is that all carbon-oxygen bonds within experimental error are the same length. Well, that doesn't make sense from this particular resonance structure, right? But these electrons don't necessarily have to belong to those 2 oxygens, right? We can have a resonance structure that looks like this. And again, I'm not moving atoms. It may look like I've just rotated the structure, but I haven't. I've kept the atoms the same. Or I can have that structure. And so the overall resonance hybrid, whoops, where's that? So how do we move electrons? What kind of arrow am I using? A double what? A double-headed, right? What does that mean? I'm moving a pair of electrons. So I'm moving a pair of electrons from this oxygen atom to form a carbon-oxygen double bond. How many bonds can I have to carbon again? 4. So if I do this just by itself, what would happen? How many bonds would I have? 5. We do not have 5 bonds to carbon. I'm from Oklahoma, and we call 5-bonded carbon Texas carbon, okay? For a couple of reasons. Number one, Texas has a 5-pointed star. That's where it really comes from. But for us Okies, it comes from the fact that we don't like Texas. And so we say they always draw 5-bonded carbon, okay? So we can't just do that, so we have to break a bond. Which bond are we breaking here? Well, now there's 2 bonds in a double bond, right? And they're not identical. There's a sigma and there's a pi. Which one are we breaking? We're breaking the pi bond. And why are we breaking the pi bond? Because it's the weakest bond, right? Weak bonds break. Strong bonds hold, right? Why is a pi bond weaker than a sigma bond? Now you learned that double bonds are stronger than single bonds, but that's the system together, right? The pi bond is actually weaker than the sigma bond. Why is that? It does have to do with orbitals. Absolutely has to do with orbitals. Which orbitals? The p orbitals. That's exactly right. And what do we know about those p orbitals? How are they aligned with each other? Yeah, they kind of just touch on the edges, right? They're not head to head like a sigma orbital is. right? And so they're weaker and they can break very easily. So we're breaking the pi bond here, and we're pushing those electrons from the pi bond onto oxygen to give it a lone pair, okay? And so the formal charge follows the electrons, and we're there with that particular Lewis structure, okay? So we've got our three different carbonate resonance structures. We've got our double-headed arrow showing that they are all resonance structures of one another. Again, these are not equilibrating structures. Don't get that confused, right? And so the hybrid looks something like that, okay? There are three equivalent bonds to the carbonate anion, meaning all carbon-oxygen bonds are equal. What's this dashed business? Yeah, it's a partial bond. It's almost, it's kind of like a double bond, but it's not quite yet, right? And so that exists all over. So if you took all three of these structures and you laid them on top of one another, this is what the hybrid would look like, right? And each oxygen atom, therefore, has a formal charge of 2/3 minus, right? There's not a full negative charge on any of those carbon, or excuse me, on either of those oxygen atoms. However, the molecule as a whole has a 2 negative formal charge, right? So we can have that in these polyatomic ions. Okay. So again, if we look at the actual data through our magic microscope, that is the X-ray structural study, we learn that the carbon-oxygen bonds are a little bit longer than a double bond, a little bit shorter than a single bond, right? Somewhere in between. So if we look at this, if a double bond, or a single bond, excuse me, is about 1.43 angstroms and a double bond is about 1.2, notice what we have for carbonate. Kind of right in the middle. You know, not exactly, but pretty darn close, right? That's what we're seeing. And so that is good evidence for this idea of resonance, that these electrons actually are mobile and can be in more places than one. And that's something that's kind of difficult for people to get. You know, that they're not on any one particular atom, right? They're delocalized over a system, okay? And so resonance theory tells us that all three of those resonance structures are equal. Each one of those resonance structures is an equal contributor to the overall resonance hybrid. Does that make sense here? Why does that make sense? Why would 1, 2, and 3 be equal contributors to the resonance hybrid?
Electrons moving between atoms of the same type, like there's no electronegativity difference.
Okay, very good. We call this equivalency. It turns out that if I put you in a room and I turned off the lights where you couldn't see anything, and I then turned the lights on and showed you this one, okay, and I rotated it around, I turned the lights back on again, you couldn't tell that I really did anything, right? These are all equivalent resonance structures, right? So you really can't tell them being different from one another. The negative charges are always on an electronegative atom that's the same type, so on and so forth. And so you end up with equivalent resonance structures. And so since they're equivalent, each one of them contributes equally to the overall resonance hybrid, okay? And so that's explained by the resonance theory. So let's summarize the rules of resonance. Again, this is a lot of refresh from general chemistry, right? Number one, resonance structures exist only on paper. Very important. They are a formality. Number two, we are allowed to only move the electrons. I have seen things on YouTube where people move an atom and say this resonance structure. That is bad form, okay? We don't do that. Don't move an atom. So for example, if we have this carbon with a positive charge, we call that a carbocation. I've got a carbon atom that has a positive charge, I've got a single bond, and now I've got a pi bond. I can draw a resonance structure for that. I can break the weak pi bond and now form a pi bond between these two carbon atoms, leaving the positive charge on this carbon. Okay? All I did was move the electrons. What electrons did I move? Pi electrons. So I can move pi electrons, I can move lone pairs, Okay? Those are the kinds of things that I can move. What haven't we moved? We haven't moved any sigma bonds. Okay? When we start moving sigma bonds, we're really starting to break bonds between two atoms, and the atoms will move. Okay? And so therefore, you aren't going to have a resonance situation. So if I have charges, if I have lone pairs, and if I have pi bonds, we can move those in a way to get resonance structures like shown here. Okay? These are resonance structures. This is not. Okay? This is not a resonance structure. What happened here? I moved a hydrogen, right? I moved a hydrogen from the end, CH3, and I moved it over to the positive charge. Can that happen? Absolutely. But that's a reaction. That is not a resonance structure because we've moved an atom. Okay? All of your structures must be proper Lewis structures. Everything you learned in general chemistry in high school about Lewis structures, Lewis dot structures is important here. Okay? You have to remember that the actual stability of the molecule will be more stable or lower in energy than might be estimated from any of the contributing structures. Very important. So for example, we have this molecule, CH3OH with a positive charge on it. Is that good? Sure. What's wrong with it? What about it? That carbon has 5 bonds. That is not a valid resonance structure, right? I see people doing this all the time. I've got a lone pair of electrons. I'll move them to the next atom. You can do that if you have something that you can break and move, like a pi bond, or you have a formal positive charge there that you can move it to. But here you can't do that because we've exceeded the octet rule for carbon. What do you all know about the octet rule? What does it apply to? And only the second row. In high school, you probably learned about this idea of expanded octet, that sulfur can have an expanded octet. I don't know why we teach that because it's absolutely nonsense. There's no such thing as an expanded 8. An expanded 8 is actually 9, 10, 11, 12, right? The octet rule can only work for the second period. Why can the octet rule only work for the second period? Okay, 8 has something to do with it. Okay, we have the s orbital, which can have how many electrons? And how many p orbitals are in the second? There are 3 possible, right? Px, py, pz. And each one of those can hold how many electrons? So 2 times 4 is 8. That's where we get the octet rule for the second period. Once I go down to the third period, I now have more orbitals to deal with, right? And so I can put in more electrons. It's not expanded 8. It's all about filling up that valence shell. That's what the noble gas rule really is. It's about getting a full valence shell of electrons. That makes things very stable. Okay? So it really is more to do with that. And then we got into talking about octet and dealing with that. And then we started teaching kids about expanded octet, which to me makes absolutely no sense. So forget it. Okay? It's all about this noble gas rule that you learned about and filling up that valence shell. Equivalent resonance structures make equal contributions to the hybrid, okay, and gives a lot of stability. So for example, if we look at these 2 resonance structures, first let's ask, are they valid resonance structures? Yes, absolutely. Everything has an octet except for the terminal carbon. And remember, carbon can have no more than 8, but it can have fewer than 8 electrons around it. And in a carbocation, it does have fewer than 8. It's not as stable as a carbon with 8 electrons, but nonetheless it can exist. And so these are actually equivalent resonance structures if we look at them, right? We see that we have a positive charge on the terminal carbon here, which looks like this terminal carbon. Okay, and so we have equally contributing resonance structures. And so what we would predict, right, is that we would have some positive charge on the ends and none in the middle. Right? So if we were going to react this molecule with a nucleophile, and we'll learn more about what that is later, where an electron pair was going to attack the carbocation, where would it attack? Would it attack the one on the left or the one on the right, or equal? Equally, yeah, it could attack either carbon with equal probability, right? And so we'll learn more about that as the semester goes on. But that's what the resonance hybrid looks like. So I don't know why my animation popped that in quite yet, but we'll deal with that in a moment. The more stable a structure is, the greater its contribution to the hybrid. Not all resonance structures are going to contribute equally to the hybrid, but all of them do contribute. Okay, very important. Typically, the more covalent bonds you have, the more stable the structure is. Okay, so if we look at this particular structure where we have this diene, as we call it, because we have two carbon-carbon double bonds that are conjugated with one another, okay, we can draw a perfectly valid resonance structure where we move the electrons here in between these two carbons and put those electrons on that carbon. Since we're moving electrons from here, that's going to make this carbon electron deficient, give it a positive charge. This carbon's gaining the electron pair, and so it gets a negative charge. Perfectly valid as a resonance structure. But is it an equal contributor to the hybrid? No. And in fact, the hybrid is like 98%, 99% this. And it has to do with the fact that this has more covalent bonds than this. What else does it have to do with? What about the formal charges? Well, it's still zero here overall. Okay, so for all the carbons, all right. But here we're talking about charge separation, right? So if we take two charges that are dissimilar and we separate them, does that take energy or does it give me energy? It takes energy. Think about it. If you take a positive into a magnet and a negative into a magnet and you put them together, they like to stick together. And if I tried to pull them apart, can I do it? Yes. But what do I have to do to get that to happen? Actually, I have to pull on it, right? Exactly. Structures in which all of the atoms have a complete valence shell are especially stable and make large contributions to the overall hybrid. So here we have a situation where we have a carbon atom with a positive charge, which is singly bound to an oxygen atom with lone pairs, which is bound to a carbon with 3 hydrogens. Okay? Now, does every atom in this structure have an octet? No. What does and what does not? This one has an octet. That's okay. Right? This carbon does. But what about this carbon? How many electrons are around this carbon? 6. So you have the 2 bonds to hydrogen, which is 4 electrons, and then the 2 between the carbon and the oxygen, which adds up to be 6. So this does not violate the octet rule, but it is less than an octet, right? Now, I've got this positive charge and I have these lone pairs. I could make a pi bond between the oxygen and the carbon. Now everything has what? How many electrons are around every atom now? 8. And every atom now has its noble gas structure. This confuses some people. Why would this potentially throw you for a loop? Why would this, you might argue, is not the major contributor of the overall resonance hybrid? You have a positive charge on the oxygen, which is counterintuitive. And why is it counterintuitive? It's more electronegative. And you would argue, well, shouldn't carbon bear the positive charge because it's more electropositive, right? It's more willing to handle that positive charge than is oxygen. The answer to that statement is true, okay? But the rule is, right, we want to have everything to have a noble gas structure. And even though oxygen here has a formal positive charge, every atom has an octet. And so this is the major contributor to the overall resonance hybrid, okay? Now, it turns out that we'll learn in another chapter way down the road, this minor contributor to the resonance structure explains its chemistry, the reactions that it undergoes, okay? But nonetheless, if we were to look at our magic microscope, we would see that the structure looks way more like this than like this, okay? Charge separation is bad. We've already talked a little bit about that, right? So here's a situation where we have a molecule where there are no formal charges. Everything has an octet and everything has a formal charge of 0. But I can take this lone pair of electrons and make a carbon-chlorine double bond and break this pi bond and put those electrons on carbon, and I can have this resonance structure. Nothing has been violated in doing so. Carbon all of a sudden doesn't have 5 bonds. Chlorine doesn't, exceed its noble gas structure, et cetera, et cetera. Okay? It's perfectly fine. But it is the minor contributor to the overall resonance hybrid because we have charge separation. We went from a molecule that has no charges to now taking opposite charges and separating them by quite a large distance. Physics tells us that's bad, to take charges that should attract one another and put a distance between them, okay? If we have resonance contributors with negative charges on highly electronegative atoms, they're going to be more stable than if the opposite is true, right? So for example, we can push the electrons in the pink direction, okay? These are not happening at the same time. This is just color coding. So what I'm doing is I'm moving the pi bond between the carbon and the oxygen, and I'm putting those electrons on carbon. So now carbon has a negative charge, oxygen has a positive charge. Or I can go with the blue direction, and I can push those electrons up onto oxygen, leaving a carbocation and an oxygen anion. Which one of those is more stable? Both of them are charge separation, so that doesn't come into play. Okay? But which one of those is more stable, the one on the left or the one on the right? And why?
The negative charge on oxygen.
Exactly. You will almost always, and by almost I mean essentially always, okay, push electrons in this manner. You always push electrons towards the more electronegative element. Okay? There are only a few examples that I'm aware of that we will never cover in this class where it actually appears to go the other way. Okay? And so, in certain chemistries. But you're going to push electrons to the most electronegative atom. Okay? And so, this is the way that we're going to do this, right? And so this is more significant than this resonance contributor. But which one of these three is the overall main resonance contributor to the overall hybrid? The left, the middle, or the right? The middle. And why? We have more covalent bonds. We have no charge separation, right? However, I will tell you, this little molecule right here is called acetone. It's your fingernail polish remover, ladies. And it turns out that this minor contributor to the resonance structure explains its chemistry. So even though we have minor contributors to a resonance hybrid, that doesn't mean we can ignore them, okay? The structure looks more like this, but this helps us explain the chemistry that we're going to be talking about in other chapters, okay? What do I mean by hybrid orbital? Is it hot in here to everybody? My gosh. We're going to open the door. Maybe that'll help a little bit. I thought it was just me. Okay, good. Good. I'm glad you're all sweating too. All right. So what do I mean by hybrid orbitals? Pardon? I can have orbitals that aren't hybrids that overlap, but you're getting there. What kind of orbitals does carbon come in with as it exists on the periodic table? S's and P's. Do you all know where they exist on the Cartesian coordinates? What's an S orbital look like? It's a ball, right? And so if I had X, Y, and Z coordinates, it would be a ball in the center, right? What about the P orbitals? There's 3 of them. Do they all lie on the Cartesian coordinates the same? They reside on different axes, right? So we have Px, which is on the x-axis, the Py, and the Pz, right? So we have 3 different directions in which those p orbitals point. And so if you think about those orbitals, you might expect that the bonds to carbon would be somewhere around 90 degrees, right? Because Px, Py, and Pz are offset by 90 degrees to one another. Yet when I look at methane, the bond angles are what? Which is what? Tetrahedral. So can those orbitals explain the bonding of carbon? Not really. We have to think about hybrid orbitals, right? And so what happens is those atomic orbitals hybridize and become new shapes, if you will, okay? So if we think about the ground state of carbon, as I mentioned, right, we've got 1s2, 2s2, and 2p2, and we've got one electron in the 2px and one electron in the 2py orbital. Does everybody remember this notation from general chemistry? Okay. What are the valence electrons here? Okay, so these in the second shell, right? The 1s we ignore. They're just the core electrons, right? They're there to hold the place to put the valence electrons where they need to be. So we've got 4 electrons that are valence electrons for carbon that we can play with, right? And that makes some sense because we see a hybrid, or we see a bonding of 4 to carbon. But if we were to use these orbitals, we might predict that at least the bonds between these 2 electrons and 2 of the hydrogens would be 90 degrees to one another. And we know that that's just not true. When we look at the structure of methane, we know that it's tetrahedral, okay? And so we have to deal with that. So what happens is this idea called hybridization. And so the ground state for carbon, just dealing with the valence electrons, looks like this. But what happens is that one of these electrons gets promoted into the p orbital, and now we have 4 unpaired electrons. And even this doesn't account for the structure of methane, because I really haven't changed how the orbitals are shaped, right? I've just changed the population of the electrons. This accounts for the bonding, because hydrogen comes in with how many electrons? 1, right? And so I can account for the bonding by doing this, but I can't account for the shape. And so what has to happen is these orbitals have to hybridize and become something different. They have to recombine. And so what happens is, right, the hybridization occurs and we get what are called sp3 orbitals. We get 4 of them. What can you tell me about this hybridization that's kind of interesting if you look on the left and you look on the right? How many orbitals am I starting with? And how many orbitals am I ending up with? 4. Orbitals are conserved. You cannot create nor destroy them. You can hybridize them, you can rearrange them, but you cannot create nor destroy them, okay? So if you start with 4 orbitals, you better get 4 orbitals in your hybridization. And that's what's happening here. We're taking these 4 orbitals and we're recombining them into 4 so-called sp3 orbitals. What does the term sp3 really mean? What does it mean? It is. It means to take 1 part s and 3 parts p and make a new orbital. That's exactly what it means. Okay? So we can have sp3, we can have sp2, we can have sp. We can actually even have sp5, which don't worry too much about it right now. It just means the percentage of p character. Will these orbitals look more like a ball or like a dumbbell? They'll look more like a dumbbell. And why is that? They've got a lot of p character, right? Exactly. So they're going to look more like a p orbital than an s orbital. Okay? And when we do this hybridization, and you think about the Cartesian coordinates, and I'm not going to do the math for it because it hurts my head. Okay? But when you do the math for that, it actually turns out that these orbitals will point in the corner towards the corners of a tetrahedron. Okay? When you do all the overlapping to get the hybrids, that's what you end up with. Okay? So this is what an sp3 orbital looks like. It looks a heck of a lot more like a p orbital than it does a ball, right? And so when we take this ball, we take these p orbitals, we put them together, we get these sp3 hybrid orbitals that point towards the corner of a tetrahedron, okay? Let's talk a little bit about sigma bonds. Tell me what you know about sigma bonds. Single bonds? Or all single bonds sigma bonds? Yeah, for the purpose of organic chemistry, absolutely, right? So what else can you tell me about sigma bonds? Pardon? Okay, that's true. When we see carbon atoms that are multiply bound to one another, one of those bonds has to be a sigma bond. What else? We can rotate around a sigma bond. Absolutely. So if I take a board and I go out to a tree and let's say I'm putting up a sign and I put one nail in the middle of the board, I can rotate that board right around the nail. What happens when I stick a second nail in the board? I can't do that anymore, right? This has consequences, structural consequences to our organic molecules. When we see a molecule having a lot of sigma bonds, it can have a lot of flexibility. And it turns out that that flexibility has a lot of meaning in terms of the type of material we make. So if you're in polymer science and you want a plastic that's really stretchy and moves and flows real easy, it'll have a lot of single bonds. If you want something that's rigid, you'll put in more structural rigidity, more carbon-carbon double bonds, etc., and other types of bonds. Okay? So if we take an sp3 orbital, for example, from a carbon atom, and I'm just showing one of them here. You've got to know the others are there as well, but just for simplicity. And I overlap that with a hydrogen atom, which just has a 1s orbital, which is a sphere. I form a bond, right? What are these colors meaning? So I can have an orbital that has a partial positive charge and a partial negative charge in the same orbital? Do orbitals have charges? These are mathematical signs that come out of the wave equation, okay? Dr. Broom should have talked to you a little bit about the quantum mechanics of orbitals, right? It actually comes out of wave theory. The good news is we don't have to solve any of that here. We just have to understand that that's where it comes from, right? And so when I have a positive overlapping with a positive, is that a good thing or a bad thing? In mathematics, that's a good thing. It means it adds constructively and it leads to stability. Again, these are not charges. And this is what confuses a lot of people, because they'll go, well, a positive and a positive should repel. That's true if it's a charge, but here we're just talking about a mathematical sign. But if I took this positive and I've overlapped it with a negative, would that be a good thing or a bad thing? That would be a bad thing. That's actually destructive interference, as we call it, and it doesn't lead to bonding. Okay? And so here we have a carbon-hydrogen bond between the 1s orbital of the hydrogen and the sp3 orbital of the hybridized carbon atom. Okay? Well, let's talk a little bit about the geometry of ethene. Can anybody tell me what ethene is? F. How many carbons? Two. Two with a double bond, the E ending, right? Okay, looks something like this. It is a planar molecule. The molecule lies in the plane that's shown there. You'll notice that the around each atom we're essentially trigonal planar, you know, within experimental error. Okay. Notice all carbon atoms kind of look the same here, right? What kind of bonds do I have? What kind of bond is between this carbon and this hydrogen? Sigma. Sigma and pi, right? Now, maybe that one's the sigma, maybe that one's a pi. We don't know. It doesn't matter, right? But we have a sigma and a pi bond. So what can you tell me about the rotation around those carbons and hydrogens? Between the carbon and hydrogen? Yeah, I can rotate the hydrogen, right? But can I rotate between the two carbons? No. Okay? Not without breaking a bond anyway. Okay? So it's very difficult to rotate around those bonds. Okay? All right, you know what? We're getting kind of long into the class today. There's a lot more that we need to go over. I'm going to cast this remaining part before Wednesday on the YouTube channel. We ought to look at before we come in and do our in-class work on Wednesday. Make sure you bring your model kit. I'll also put the stuff that I've just talked about on the YouTube channel as well. I want you on your card, on the front of it again, please print your name and your ID number. Did you not get a card? Anybody have the extra cards?